So hi everyone. Just wanted to give a quick shout out to Paige and Courtney for organizing the whole event. So thanks again. But as Guy was saying, my name is Ryan West. To give you a little more context for who I am, I'm a graduate from Knox College, which is a liberal arts college in the middle of nowhere, Galesburg, Illinois. I'm also a graduate of Washington University in St. Louis from the System Sciences and Engineering Department. And I am currently a Venture for America Fellow, which is a program for young professionals who are aspiring entrepreneurs, and they provide the resources and ongoing training as part of the program. And so becoming a Venture for America Fellow is really what helped me find my current job at Nexosis as a data scientist. So at Nexosis, we have worked on automating traditional data science workflows and putting this into an API. So it's a machine learning API specifically for developers, and you don't need to have any experience in data science or mathematics to be able to use it. You just have to be able to submit your data set, and we'll do all the heavy data science lifting in the background and give you what you really want in the end, which is just your forecasts or predictions. So working at Nexosis and on these types of problems, you can imagine there's a lot of automation that goes into our engine, and so my talk is tangential to that mission. So I will be talking about automating time series model selection. So something I'm sure many of you in the room are intimately familiar with is the idea of k-fold cross-validation, randomly mixing up your training set and creating different partitions of your data and training and testing until you get the optimal model. Well, this works great for cross-sectional data, but it doesn't generalize well to time series modeling. And so for time series modeling, you have to do a little bit different of a process to cross-validate a model. You have to do this rolling cross-validation technique where you say, build a model on 50% of your data, test on 10%, and that 10% is sequentially arranged relative to your training set. So you have to make sure that your training and test sets are kept in this sequential order. And as you can imagine, this can be quite computationally expensive, although it might be worth it depending on what your application is. So an alternative to doing this rolling cross-validation technique, the simplest technique would just be to create a model and test it once, but clearly this can have ramifications too, right? Because you will be potentially overfitting to your test set, which could lead to selecting an unbiased model. So there has to be somewhere a middle ground between using this rolling cross-validation technique and simply testing on one test set. And so that's the idea of training, validating, and testing, which I'm sure you're all aware of, which in the field of time series amounts to making sure you have your training set, validation set, and test set temporally arranged one after the other. And so this is sort of the process that I've been trying to automate. And when you think about it, what typically goes into model selection when it comes to validation and testing is, say, building a model on your training set, looking at the error metric on your validation set, and looking at the error metric on your test set, and making sure that both of those error metrics are low. And if both of those error metrics are low, you know you probably have a good model. But you'll keep doing this process to see if you can get better validation and test set metrics. But then there's also the scenario of perhaps having a relatively higher error metric in your validation set and a lower error metric in your test set. So it's kind of unclear what you do in that scenario. Do you throw the model out? Do you save it maybe for use later? So what I'm proposing is a solution to streamline the process into a minimax problem. And so instead of just having one test set, you have many test sets represented by this lower layer, and you break these test sets up into your validation set, your test set, and really any number of arbitrary test sets. And so that's the bottom layer of this node. And then for these collection of test set subsets, you build various models and produce forecasts across all of those test set subsets. And so mathematically, this looks like a minimax problem. You have a random variable x for each node, and this variable x can take on n possible values. And so this variable x is an error metric, and it's calculated with your n test sets and the forecast of model I. And so this is equivalent to this linear program shown here, minimizing some variable s, subject to the constraints that s must be greater than or equal to each of your variables. And so really, to sum up this whole process, it's a model selection algorithm that chooses the least worst algorithm in the hopes that it generalizes better than just choosing the model that just so happens to perform the best on one single test set. And you can formulate this differently as well. Instead, you would replace your bottom layer nodes in the middle and formulate it as a maxi-min problem, which perhaps makes less intuitive sense to, at least it does for me, because why would you ever on Earth want to maximize an error metric? However, it is mathematically identical to the previous formulation I described above. And so what really it comes down to is picking the one that's easier to implement. And so for my purposes, in the experiment I've been testing on, it just so happened that I had all of my forecasts for various models grouped by these various test set subsets. And so it made more sense, or at least it was easier to implement and use this formulation, even though it was a little less intuitive, because I knew it would give the exact same results. And so what is this experiment I've been describing? It's an experiment where I took roughly 856 curated time series of daily retail sales data, where each time series had 7 variables exogenous to the target time series. And so these are variables like whether there was a promotion, what holidays were occurring, and other indicator variables of that nature. And for each time series, I use a brute force method of just using completely just a wide selection of models. So through an autoregressive neural nets with different types of seasonalities, down to simple ARIMA or exponential smoothing algorithms. So this experiment was less about having the correct algorithm, and it was more about throwing in a number of different models and seeing if this mini-max model selection can choose the right one. And so the hypothesis is really just that can this mini-max model selection algorithm yield results that are comparable to, say, simply choosing a model based on minimizing some error metric in a single test set. And so these are the different types of model selection techniques I employed for this experiment. So I used selection using ensembling based on choosing models based on minimizing different error metrics. And I also tested, of course, this maxi-min or minimax algorithm I've been describing, as well as the typical using one test set and minimizing the error metric over the set. And there were a few assumptions going into this modeling process. So most of the time series showed very highly partial autocorrelation, specifically for 7-day lags, 14-day lags, 21 and 28-day lags. So it's very clear that the data is very weakly seasonal. And one might also think it's biweekly or tri-weekly or monthly seasonal as well, but you can tell by the first partial autocorrelation plot that the peaks start to die down over time, which indicates that the time series is predominantly weekly seasonal only. And then looking at another partial autocorrelation plot, you'll notice that there's a very high peak at 365-day lags, which indicates that the time series are also very annually seasonal. So when actually modeling these time series, these were the primary seasonalities used. And so, like I said, there were roughly 1,000 time series I used in this experiment. For each time series, I had 3 independent test sets, so a validation set, a test set, and then an additional test set just to test this minimax algorithm. And then for each time series, I also employed roughly 40 models. So overall, there are roughly 100,000 measurements for error metrics over all these different test sets. So here's a visualization of mean absolute error plotted as a histogram of these 100,000 test sets. And so you'll notice some interesting things about it. For one, it surprisingly looks exponential or Poissonian based. Or another way to interpret it is that it seems as if there are a few models that appear to perform very well over their test set. There are a decent number of models, or there are commonly performing models at that red vertical line. And then the majority of the models seem to actually perform quite poorly. And so you'll notice there are 3 lines indicated. Orange line is the mean, blue line is median, red is the mode. So the majority of the models to the right of that red line indicates poor performance. And here's another visualization using root mean squared error. So you'll notice it also follows the typical pattern shown above. And the actual metric I used for the minimax algorithm selection was root mean squared prediction error, or sorry, root mean squared percentage error. The reason being that it does not include actual values of 0 when producing the error metric. And the reason this was very important for this experiment was because there were a lot of zeros in the time series, meaning that there were days when these retail stores were completely closed, and so they had no recorded sales on these days. And so really measuring performance on these days were kind of worthless, right? Because we already knew 100% that these results are going to be 0. So that's why there's a high spike at 1.0. And then we see a slightly different pattern for SMAPE. And SMAPE is sort of a biased but unbiased error metric, in that it's touted as being a metric that shows symmetry relative to your target, but in actuality, there is no real symmetry. It's more biased towards selecting algorithms that underestimate your target. So here's just a visualization of the different error metric for SMAPE, but I ended up not using it for model selection because of its uncharacteristic nature. And so the final results of this experiment showed that minimizing root mean squared percentage error on just one test set actually did perform better than using this minimax algorithm I've described. But as a proof of concept, it looks like this minimax algorithm didn't do much worse than just simply minimizing your test set. And it looks as if it performed better than just simply using a naive weekly seasonal predictor for every time series, which was actually a pretty decent assumption going into this modeling process, right? Because every time series seemed to show very highly weekly seasonality. And the other method I tested was ensemble averaging, which seemed to perform the best overall. But perhaps for future research into this topic, it looks like the shape of these distributions is highly important for determining if you should even use a minimax algorithm selector. For example, looking at the mean absolute error distribution, it's highly right skewed. However, if it were more Gaussian based, then this minimax algorithm might intuitively make a lot more sense to employ. And similarly, if it was left skewed, it might not make sense to use this minimax algorithm at all. So it is not an algorithm that should be used for every time series type of forecast, but it's definitely conditional on the distribution of these test set distributions. And so I just want to say a quick thank you to everyone who attended today, and appreciate everyone who stopped by our booth, and congrats to the winner of the Cosmo robot, and sorry to everyone else who did not win that Cosmo robot.